talk about it, but that's not what he requested me to talk about. So,
All right.
but yeah, it's right along. So,
well, maybe what I'll do is just say a couple introductory things here that I was thinking about talking about, and let people know that there are some additional YouTube videos if you want to go onto the Ice Age Floods website,
yeah.
iafi.org. And I just looked a few minutes ago and it looks like there's about 21 on there so far, but continue to have more as more chapters have presentations online. And another thing I'd like to talk about just briefly is that the Park Service is actually, after 12 years, I think it is finally come up with what we call the Unigrid map, which is the map when you pull up to the park rangers kiosk or at the park entrance, they hand you for the park. And so the one for the Ice Age Floods National Geologic Trail has been finalized. And so after that was, 2009 was when the legislation occurred. And so now it's 2021. So 12 years later, we're getting it done. And so what I'm hoping is that, and just talking with Mariah Thornack from the museum a little earlier, that we potentially could have, the museum potentially could open up at the end of June when Washington State opens up. And I'm not sure if that's going to allow us to have a meeting in August or not. So that's something we have to decide. But at some point when we're all in together in the setting in the museum, then we will share that Unigrid map, a copy of that with everyone. So something to look forward to. And also to look forward to is that I was at the museum yesterday and it's gone through some pretty good renovation. There's a lot of new paint and new lighting and new computer system, new audio system, new audio visual system. And so when we get back in there to have presentations, it'll be a great thing to utilize when we get there. So just a little plug there that you'll see a lot of improvements when you get back to the museum. They added a little side room on to the stage, kind of as a prep room, and also kind of a ramp there for handicap accessible, wheelchair accessible area. So let's see here. Well, we're up to 9 now, so let's see. I think that's about all I really wanted to say. So I guess I'm gonna shut off my audio, and if you want to get started on your presentation, I guess we'll do that.
Sounds good. Hold on just a moment. There's always a little turn on one thing, turn off the other so that you can actually get rolling on this. So hold on a second. Okay. All right, so hopefully all of you see a screen that is not my notes screen.
Yeah, we can see
Brent,
it.
do you? Okay,
yeah.
Great. Okay, well, so I'm Kelsey Stanton. I think everyone who I saw in the attendees list knows who I am, but I am here tonight to talk to you a little bit about earthquakes in the Pacific Northwest, and to kind of follow on that. Who am I? In case there's someone there who doesn't know, I am a member of the Erratics. I haven't been over in your neck of the woods for a couple years because I am also currently a PhD candidate at University of Washington. And so Ken Lacey had come to a recent talk of mine called a general exam, which is actually what I had to give in order to officially become a candidate. And it was about my research, and he contacted me afterward and asked to be willing to talk a little bit about earthquakes in the Pacific Northwest, because my research is loosely related to that. So tonight I'm not going to be talking about my research, but about earthquakes in general. And so you know a little bit more about me. I'm a structural geologist and also a quaternary geologist. And so structural geology is the study of faults and folds. And in particular, what I'm interested in thinking about is how faults and folds can tell us about past geologic events. And I also work mostly in the quaternary, which is the past 2 million years. And so I'm really interested in the faults and folds that have been active in the past 2 million years, because they are likely still active. And that tells us something about our potential hazards, and also what the plate tectonics in our region are doing right now, because 2 million years is recent in geologic history. So tonight, I am going to start by just giving us a quick rundown of what we need to know in order to think about earthquakes in the Pacific Northwest. So faults, earthquakes, and recurrence intervals. Then a really quick and dirty plate tectonics, and specifically about subduction zones, which are really just big faults. And then talk about the 4 main seismic sources or earthquake sources in the Pacific Northwest. So megathrust earthquakes, the big one. Deep intraplate earthquakes, like the 2001 Nisqually earthquake. Upper crustal earthquakes, like our very own 1872 Central Washington earthquake, and also the 980 Seattle earthquake. And then a recent seismic source that we've only known about for about 2 decades, called episodic tremor and slip and slow slip earthquakes. We sometimes just lump all this together and call it episodic tremor and slip, ETS. And then I'm going to briefly talk about hazard and risk from earthquakes. So we have to start by thinking like structural geologists. So structural geologists think about stress and strain and how that's expressed in the geologic record. So the stress first, then area feels. So here I have a box with no stress. And when I put a tensional or extensional stress, that's the stress pulling that block apart. Right? I can have compressional stress, that's stress coming together. And I can have shear stress, which is stress moving sideways apart from each other here. Okay, so stress can cause deformation, and we call that strain. And I've actually shown strain in all of these different blocks. But here we have a block with no deformation, no strain, but I am exerting a stress or a force in form of this red arrow. We have 2 kinds of strain. We could have plastic strain, which is where the block is deformed, in this case squished down, right? We could also have brittle stress, where the block doesn't compress, it doesn't change volume, but it breaks. And there's a 3rd kind of stress, which is elastic stress. That's when your block would deform, and once the force is removed or that stress is removed, the strain would rebound. In other words, you'd have elastic rebound to that. But that rarely happens in geologic materials, so we won't even think about it. We just think about plastic and brittle. And all of these blocks are exhibiting plastic strain. But when we think about faulting in earthquakes, we're actually thinking about brittle strain, so something breaking. So a fault is a fracture or a zone of fractures between 2 rocks, and it's a result of brittle strain. So it's a fracture in the rock itself. And any movement on that fault results in an earthquake. So here we have 2 blocks of rock. Here's our fault plane. And when we have movement, we have an earthquake. It's at some depth. And we generally call that the hypocenter. It's at depth. And we project that up to the surface, and that's the epicenter. So when there's an earthquake, when we're talking about the epicenter, that's the projection of where the earthquake is on the surface of the Earth. And faults come in all kinds of sizes, from just a few meters up to hundreds of kilometers long. So what is the earthquake on that fault? Well, it's a release of energy during slip on that fault plane. And the energy release, we describe it in terms of magnitude. And now this is an issue that has actually plagued us for years, because most people hear earthquake magnitude and they think Richter scale, but the Richter scale is actually a form of earthquake magnitude measurement that is really only used in California, or should only be used in California. It was developed just for faults in the specific kinds of rocks in Western and Central California. And it really is only good to think about earthquakes, compare earthquakes in California itself. So instead, what geologists and seismologists more frequently use is what's called moment magnitude. And this is a measurement system that allows us to compare earthquakes globally. And moment magnitude, or M sub W, is proportional to the amount of slip and the area of slip. So if we have a really long fault and it slips a whole bunch along its fault plane, it's going to release a large amount of energy and there'll be a large moment magnitude. A shorter fault, or maybe a long fault that only slips a small amount on its fault plane, will release less energy and it will be a smaller moment magnitude. We think about moment magnitude in log scale. So a magnitude 2 earthquake releases approximately 32 times the amount of energy as a magnitude 1 earthquake. So it gets big fast. And I realize now that I'm seeing this is a bit fuzzy when it's in larger screen size here, so I apologize for that. But up here, above magnitude 9, we have the Chilean, the Alaskan, the Sumatran earthquakes, very large, greater than magnitude 9 earthquakes. Here's our 1906 San Francisco earthquake, just under a magnitude 8. We have lots, just innumerable magnitude 2s and 3s every day around the globe, and so they don't even show those ones. And to compare that, Krakatoa eruption and the world's largest nuclear test, Mount St. Helens eruption, those are all between magnitude 7.8 and about 8.5. The atomic bomb was right around a magnitude 6 in the amount of energy it released. And a large lightning bolt releases about the same amount of energy as a magnitude 3 to 3.5 earthquake. And so these are earthquakes that most people can't even feel. I usually never feel magnitude 3s. Occasionally there are some people that do. So that's a large lightning bolt. So that gives you an idea about the energy equivalency for these magnitudes of earthquakes. So one other thing we have to talk about before we get on to the earthquake sources themselves is recurrence interval, because I'm going to be talking about that a lot. So recurrence interval is something that we talk about when we're thinking about any kind of hazard, and it's basically how often does it happen. So for earthquakes, an earthquake recurrence interval is the number of years that you're considering divided by the number of earthquakes. So let's say we had an earthquake in 1700 AD, one around 1310, 810, 400, one in 170 BC, and one in 600 BC. Okay, so the time period that we're thinking about is 2,721 years. There's 6 earthquakes. So that gives us a recurrence interval of 453.5 years between events. So if the last earthquake was in 1700, does that mean that we still have a lot of time before we have the next one? Do they happen just every 453 years? Well, no, obviously, when you can look at this interval here, it doesn't mean that there's always exactly 453 years between events. Sometimes it's nearly 600 years. Sometimes it's, only 390 years. Okay, so this is an average. The average amount of time between earthquakes is what we're talking about with the recurrence interval. It could be much larger or much smaller than the actual recurrence interval time. And the way that we figured this part out over here is based on geologic evidence. So I'm going to talk about megathrust earthquake, pardon me, in just a little bit. But these calendar years that I actually presented over here are when we think we had megathrust earthquakes on our subduction zone. Okay. So quick and dirty plate tectonics, and then we'll jump into the earthquakes themselves. The outer part of Earth is covered by brittle, rigid plates. They move around Earth on top of a less brittle, a more malleable asthenosphere. And plates can move past each other in 3 different ways. So we can have plates that slide past each other, and those are called transform plate boundaries. They can move away from each other, and that's called a divergent plate boundary. Or they can move toward each other, and that's called a convergent plate boundary. And the convergent plate boundary is what we're really interested in tonight, or what I all the time am really interested in because of work that I do here in the Pacific Northwest. So we are at a spot where an oceanic plate is converging toward a continental plate, and the oceanic plate is more dense, and so it gets pushed underneath the continental plate, and that's called a subduction zone. And I'm sure you folks have heard about this, and we are on a subduction zone. It's called Cascadia subduction zone, or sometimes we just call it Cascadia short. And so out here we have the Juan de Fuca plate moving away from the Pacific plate. This is actually a divergent margin out here. Okay, and the Juan de Fuca plate is moving generally to the east, and the North American plate is moving to the west-northwest. And when they converge, the Juan de Fuca plate gets pushed underneath the North American plate. And out here, right where they meet, is called the subduction margin. Okay. So this subduction zone has a role in all of the different kinds of earthquakes that we feel here in the Pacific Northwest. And so when we have earthquakes right on the plate interface between the Juan de Fuca plate and the North American plate, it's like a really big fault boundary, right, between 2 blocks of rock. These are called megathrust earthquakes. We also have deep earthquakes that are in this downgoing subducting plate. These are deep intraplate earthquakes. There are faults in the North American plate. These are called upper crustal faults or upper crustal earthquakes. And then in the past 2 decades, we have noticed this phenomena of tremor and very slow slip earthquakes. It's kind of highlighted by this pink here. It's called the EDS zone. This is where they tend to occur. And as far as we can tell, in depth in this cross-section view, they occur just right above this plate interface. Okay, so I'm going to talk about all of these different kinds of earthquakes. We're going to start with the megathrust earthquakes. This is what the big one, when we're talking about the big one, it's in the Pacific Northwest. This is what they're talking about. And this is what some years ago, there was an article in the New York Times, I think that, or no, the New Yorker, about the big one. And it scared all kinds of people. There were people who moved back into tornado country, which happens every year. I don't know why they did that, but this is the hazard that we refer to as the big one here on our coast. So what's going on? Well, the subducting Juan de Fuca plate becomes stuck or locked against the North American plate here. And because it's locked, but there's still a stress from this direction, it actually causes the North American plate to uplift a little bit. And eventually this slips and this downgoing plate releases, and this causes a very large earthquake. This is generally up to, this is in the upper 15 kilometers of this plate interface. And so it can be a very large amount that slips, and also a long length. Usually not the entire plate subduction margin, so not all the way from Northern California up to Canada, but still a very large length. And so these are very large magnitude earthquakes. When that earthquake occurs, the portion of the North American plate that was uplifting subsides very rapidly. And out in the ocean, there's a little bit of uplift related to this. And this little bit of uplift can cause a tsunami. Okay, and these megathrust earthquakes, they happen on other subduction zones. This is what the Chilean earthquake was, and the Alaska earthquake, both those were in the 1960s. This is what the Sumatra earthquake and the Tohoku Ono in Japan in the 2000s, they were these large megathrust earthquakes. So how do we know that Cascadia has these? Because we haven't had one of these while there have been white settlers around to write about them. Well, primarily we know from buried marsh soils and tsunami sand. So here we have a dune sand with the topsoil on it and some fire pits used by natives. This isn't showing, but often the topsoil has plants, dead plants within it. And above that is another clean sand and tidal mud above it. Okay, so what has happened is that this portion down here, the sand and the topsoil, was on the portion of the coast that was uplifted while these plates were locked. Plants were growing on it. And then the earthquake occurs and that entire area subsides very rapidly within seconds. That earthquake causes a tsunami, and the tsunami water rushes in to inland, depositing a layer of sand. And now this entire area is below sea level again, or at least near it. And so it becomes a tidal marsh area, right? From this photo, you can see grass growing up here, right? This is now back above sea level. This is part of the evidence that we have that it is currently uplifting from that plate being locked again. So Brian Atwater and others, they took some dead plants from locations these and they dated them, and they came out somewhere around 1700. So we know that there was one of these very large earthquakes. There's also a native history tsunami. So over here I'm showing, this is depicting the story of the thunderbird fighting the whale. This causes a bunch of ground shaking. And this tradition, this oral tradition, teaches people that when they feel the ground shaking from this fight between the whale and the thunderbird, that they need to run inland and up hills because water is going to rush in. So there is a native history about tsunami. We actually know that this tsunami, this earthquake, happened in January of 1700, very specifically, January 26th. And you can't get that from dating organic material, but the Japanese actually record all the tsunami that come into Japan, and they had an orphan tsunami. So in other words, it was a tsunami that came in, but there wasn't any previous shaking right before it. And they wrote down the date and the time. And Brian Atwater worked with some of these folks, and he backtracked the amount of time it would take for a tsunami to reach them. And it corresponds with some of the potential overlap from the carbon dating. And so they have a very exact date of at least the last megathrust. Finally, we also have an offshore record. So this is all onshore, but we have an offshore record where turbidites, or kind of underwater mud flows, occur during earthquakes or as a result of an earthquake. They can also occur from very large storms, but we do have a record of these that we can date the organic material as well. So we know that Cascadia has had megathrusts. How often do they have them? Well, the sequence of buried soils all along Cascadia suggests that recurrence intervals are between 300 and 700 years. So this is a photograph actually from Johns River out near Grays Harbor, which is my field area, even though this is not specifically what I am working on for my research. And each of these little lines here are showing buried soils. So we know that there's a sequence of these occurring over and over again. These megathrusts may occur as smaller releases. So in other words, a portion of the downgoing plate may release, another may stay stuck and then release later. And so it's possible that there's different recurrence intervals all along the Washington coast. All right, so now let's think about stuff that we have historical seismicity. So things that we know about because people recorded it either with seismometers or have written about it. Okay, so this is showing earthquakes between 1969 and 2003. Here's our Juan de Fuca plate. Here's the margin right there. All of these filled circles, the little filled circles, are earthquakes that are occurring in the subducting plates. So in the subducting Juan de Fuca plate, also in the subducting Gorda plate, and up here off of this subducting Explorer plate. So there's some other small plates that are being subducted under. The open circles show crustal earthquakes. So these are the two that we're going to talk about next. Earthquakes in the subducting plate and those in the upper crust. So deep intraplate earthquakes, they're occurring in the downgoing or subducting plate. They're probably related to faulting from bending of this subducting plate. So as the plate gets forced under, it begins to bend. That bending, remember, these are rigid plates, and that bending causes fractures, and these are probably earthquakes within that. And in the Pacific Northwest, we've had quite a few of these with 1949, 1965, 2000. The most recent was in the Squally earthquake in 2001, February 28th, 2001. It was a magnitude 6.8, and it occurred at a depth of 51 kilometers, almost 52 kilometers. So the hypocenter was at a depth of 52 kilometers. And it caused quite a bit of damage. Probably, if you lived in the Pacific Northwest, you remember this happening. I was in Corvallis doing my undergraduate work. I clearly remember this happening. You know, most people that were alive and over 5 at this time remember it. I've had lots and lots of students tell me about it. However, I'm getting older, students are getting younger. There's fewer and fewer of them that remember this, but probably most of you. So it did cause quite a bit of damage. These deep earthquakes occur fairly frequently. So there's lots and lots of very small ones. So magnitude 6 and less, those happen quite frequently. But the magnitude 6 and above probably occur or seem to occur about every 30 to 50 years. And the last two previous to Squally were 1965 and 1949. These are both images from the 1965. So this is out along Everett. You can just see it, this little landslide just failed right underneath the railroad there. And this is in Seattle itself, just a nice big opening up of you know, some of these streets are built over empty areas, if any of you have done the underground tour, and so there's just failure there. So it's possible some of you also remember the 1965 deep earthquake. These, because they occur frequently, can be very damaging, but they rarely get over a magnitude 6 or 7. They're just so deep that the energy has to travel so far that the magnitude and the amount of shaking from them is not usually as much. Okay, so now on to upper crustal earths. These are our very own Central Washington 1872 earthquake and the 900 Seattle Fault earthquake. There's many others, but these are just 2 examples I'm going to use. And these are occurring in the overriding plate. And we have to know a little bit something about how the Pacific Northwest overriding plate, or the North America plate, is feeling stress in order to understand why these faults are where they're at. So in the Pacific Northwest, we have a general rotation of Washington and Oregon around a pole that is kind of, maybe in Washington, I think it's more recently been placed right down here. It's kind of rotating around this pole. So the Sierra Nevada tectonic block down here, it is translating to the northwest as a result of the San Andreas Fault on this side and the Walker Lane fault zones on the east side of the Sierras here. So it's moving slowly to the northwest, and it hits the edge of Oregon and starts to cause the Oregon block to rotate. And that causes the Washington block to rotate. Both of these hit the backstop of stable North America and Canada. It turns out this is not that stable, but it's more stable than everything down here. And so it hits this backstop. And so this is sort of like if you slid along a rug and the rug hit the wall on the other side and you kept sliding, it's going to cause a bunch of ripples, like a crumpled rug. And those ripples we see as faults. and folds. So we have the Yakima Fold and Thrust belts, and we have a series of faults from Portland area all the way up to Canada that are generally east-west trending, or maybe northwest southeast trending. And these are the faults where we have these upper crustal earthquakes. So this is the Quaternary Fault database. It shows it's active in the last 2 million years, and it's not recently updated. I think the last time it was updated was 2006 or 2010. Missing a lot of more active faults that we've found since then. But in general, you could see that Washington has got a bunch of sort of east-west trending faults, and the orange are active in the last 15,000 years. Green are in the last 130,000 years. Blue, which there's more of them down here in Oregon, are the last 750,000 years. And the black are undifferentiated ages. However, some of these have been confirmed to be either in the last 15,000 or last 130,000 more recently. So we have a lot of active faults in this region. And they produce earthquakes. So one of the famous, and in fact, the largest historical fault in Washington, or earthquake rather, largest historical earthquake in Washington was the 1872 Central Washington earthquake. And it occurred, at the time, all we knew was between, and until recently, it was somewhere between Wenatchee and Chelan was the epicenter. And that was based off of reports from shaking. So a variety of scientists looked at all of the documented descriptions of the shaking and said, well, it occurred somewhere around Lake Chelan. And, you know, a lot of people wrote about it. So down here, Charles Lombard, he wrote about how it made the houses rock, shook down a portion of the plastering in the new boarding house. Mrs. George L. Mattoon was frightened into sickness and has not yet been able to recover. So it's this great, you know, late Victorian or mid-Victorian version of what a lady who gets frightened by earthquakes into sickness. We're beyond obvious. I'm pretty excited about earthquakes, but regardless, the microseismicity. So first of all, the shaking records suggested it was near Lake Chelan, and the microseismicity, all the small earthquakes that are still going on in the Chelan seismic zone, suggested a fault somewhere near Chelan. But really, if you talk to people in our area, you know that those minor earthquakes are actually felt more frequently right around Iniad. It may be called the Chelan seismic zone, but it's really, most of them are felt right around Iniad. And so more recently, in the past couple years, Brian Sherrod, who's a US Geological Survey geologist, decided that he needed to find the fault that actually caused this earthquake, if he could, if it happened to break the surface. And so he started looking at LIDAR. And LIDAR is a way of looking at the Earth. It's shot from a laser shot from a airplane, hits the ground many, many times, and you can process that, and it gives you an image of what the Earth would look like without any vegetation on it. It is a geologist's dream because it means there are so many things that we can see. And so he looked at the LIDAR for the region. He and some other geologists, and one of them, who happens to now live in Wenatchee, happened to notice, Brian Sherrod doesn't live in Wenatchee. Sorry, Ralph Hagerud is one of them who he spotted this. He lives in Wenatchee. He happened to be sharp-eyed enough to spot this little feature right here. And I'm pointing to it with all of these red arrows. Here's 97A, here's a Rondo, here's the Columbia River, and this is Spencer Canyon. There's a little house right here, and you don't access Spencer Canyon. Well, you could access it, but the road doesn't go up this way. You usually access it from the Iniad side. And so this looks like a rupture of fault on the surface. And Brian Sherrod actually dug a trench across fault off this photo. You can actually go to the Washington LIDAR portal and zoom around and look at all this LiDAR, it'll just blow your mind. So you could go look for it yourself. You probably won't be able to see the trench, but you can follow this all the way up. And he dug a trench across this fault and saw that it was offset. And he happened to find a couple ash layers, one from Glacier Peak, maybe one from Mount Mazama, but he found some organic material and he dated that. And this is a tail of a little landslide that crosses over this fault, and it blocked a pond and killed some trees, and he dated those trees. And the landslide actually has trees growing on it, so he cored those trees and counted the cores. And all of that information said that this earthquake, this fault ruptured within 20 years of 1872. And since there were folks in the region 20 years before and 20 years after, and that was the only earthquake that happened in that 40-year period, this is likely the fault that produced the 1872 earthquake. So that's pretty exciting. The largest fault in our region, probably about a magnitude 7.1. Okay, and so now we're looking at LiDAR again. We're thinking about a different earthquake. Here's Pioneer Square in Seattle. This is West Seattle. This is Bainbridge Island. This is LiDAR. And you can see these features right here, okay? And these are faults that are related to the Seattle fault zone. Again, Brian Sherrod, he's our local celebrity when it comes to this. He has done a lot of work on some of these fault strands. And looking at these fault strands and thinking about also dead trees caused by a landslide over in Lake Washington, it would be off of this. They have a date for the last earthquake on the Seattle fault zone of 900 AD. And it was a massive event, probably around a 7. And in fact, this little spit of land right here, this is Alki. So if you go over to West Seattle, this is where people are walking and playing on the beach. This was uplifted as a result of that earthquake. So in this general area, everything south of it was uplifted, everything north of it was down dropped, and it uplifted probably about 3 meters or 9 feet. So quite a bit. We don't know exactly where the Seattle fault is. Some people put the main Seattle fault pretty far north by Pioneer Square. Others have it more around West Seattle here. It probably is at a depth. It probably doesn't totally break the surface, unlike these little splay faults off of it. Okay, so this is another major crustal earthquake. How often do these occur? Well, faults like the Seattle fault, the Tacoma fault has a fault too, Southern Whidbey Island faults, these probably have earthquakes in clusters. This is what Brian Sherrod and some workers think. So they've looked at a lot of the data. It appears that there are several large earthquakes within several decades on these faults, and then several thousand years of quiescence. So possibly some rearrangement of the stress in the strait field from a cluster of earthquakes. And then it takes a while for the stress to build up before there's another earthquake. The Spencer Canyon Fault does seem to be an exception because we do know that we've had that one earthquake on it, not any before or after, except for the microseismicity. Most of these faults have between a magnitude 6 and 7 earthquakes, so a fairly large fault, releasing quite a large amount of energy. There's microseismicity that's common around some of these upper faults, and this is a case for our Spencer Canyon Fault, right? This is the Chelan seismic zone, but they actually think that all of those small earthquakes that are felt from Wenatchee to Chelan are probably still aftershocks from the 1872 events. So everything is slowly readjusting itself. You know, this is a big release of energy. There's a lot of other smaller faults that maybe feel the stress and have some movement. And so those are probably all aftershocks. I think that's pretty amazing. Okay, so finally, we're going to talk about this zone right here, the episodic tremor and slip zone. It's also called slow slip earthquakes. And these are events that we only have known about past 2 decades or so. And so these are small tremors. They're called non-volcanic tremors. So it's a little bit of shaking or movement and it's not associated with volcanoes, although we also see tremors with volcanoes. These are all non-volcanic. They occur in swarms lasting several weeks. So this is showing from 2010 to 2020. And over here is latitude, so Northern California up into Canada. We can see these swarms, and these generally migrate parallel to the subduction zone. So they start sometimes in the north and migrate south, or vice versa. They are measured seismically, so we can actually see this in the seismic record. I'm showing these here, but we also can measure it with GPS. So we can see a movement of some of the GPS stations, or displacement of these GPS stations. And then after one of these swarms, our GPS station is back where it started, and then we see the movement again. Okay, so since we recognize this, we've seen them quite frequently. And this is showing tremor all along our plate boundary. So all of these represent tremor. But then this is using, thinking about it in terms of density. And you can see that there's a large density of tremor in northern Washington and Vancouver Island, and also Northern California. Not as much in Oregon. It looks like there's a lot, but there's not as much when you actually look at it. And then this is showing those gradients, basically putting lines around some of these very large changes in tremor density. What Ray Wells actually was trying to describe here is that many of these locations, these gradients, correspond with locations where we happen to have upper crustal faults. And he thinks there's some connection, but not everyone does. And that brings us to what is causing this episodic tremor and slip. And this is sort of, right now, one of the million-dollar questions in Cascadia seismicity, because there's a lot of suggestions, a lot of ideas. So in 2014, Schmalzel and others thought that maybe it was a rock type which was blocking water flow into the overriding plate. So these episodic tremor and slip appear to occur right above the plate interface. And so here is up in the Olympics, the rock type is allowing water to move into the overriding plate, and that's causing the tremor. That's what they suggest. Whereas in Oregon, the rock type is preventing that from happening, and so you don't get the same amount of tremor. That's how they explain that. In 2015, Hinman and others suggested that very deep metamorphosis of the subducting crust, down here where it says eclogitized crust, this metamorphism releases water from minerals, which we know happens, and they suggest that that actually causes water to migrate up and then causes tremor. More recently, Kaylee Condon suggested that the basaltic crust itself that's being subducted, it doesn't even have to get to very deep depths in order to release water. It can actually release water right where the ETS is happening itself. So there are many, many suggestions of what might be going on here. As I briefly mentioned, Ray Wells thinks that maybe the location of upper crustal fault plays a role in this as well. One thing to note is that all of these people here are related in one way or another to the Pacific Northwest at University of Washington or University of Oregon, or the USGS are located up here. So this is something that people in the Pacific Northwest are spending a lot of time doing active research trying to think about this. And we do get ETS in other subduction zones, but there's a lot of work in Cascadia right now. We have a lot of site systems able to measure this, and so there's a lot of work. It's pretty exciting. You can head to the Pacific Northwest Seismic Network, PNSN, and they let you know when these episodic tremor slip are starting. We can't feel them, of course, but they usually last several weeks and occur 14 to 18 months apart. And so PNSN is a good place to check that out. All right, so now I want to just briefly talk about hazard and risk from earthquakes. So a geologic hazard is any natural earth process that causes danger for humans or their infrastructure. So earthquakes, floods, landslides, you know, if they happen where there's no people, they're not actually a hazard, right? They're just a process. It's kind of like the tree falling in the woods kind of thing there. Well, risk is the chance that a geologic hazard might cause damage to humans and their infrastructure. So risk is based partly on recurrence interval, how often these things happen, but also on the humans and the infrastructure that might be affected. So some cases, population density is a big part of risk. As an example, over here I'm showing the Denali Fault, 2002 Denali Fault, magnitude 7.9 earthquake. Okay, south of Fairbanks is where the rupture occurred. It had a rupture length of 209 miles. It was really long rupture length. That's why it was such a large magnitude event. There were no deaths from this, and there was minimal damage to infrastructure. And it's partly because the only infrastructure is this Trans-Alaska oil pipeline. And they actually have the pipeline on rollers where it crosses over the Denali Fault. They know the trace of it. And it moved on its rollers and it didn't even break. It was pretty amazing. Contrast that to the 1906 San Francisco magnitude 7.7 to 8.3 earthquake. We don't know exactly the magnitude because we didn't have devices to measure, the amount of shaking. So we're making an estimate of the magnitude. The rupture length was about 296 miles, so very long, but again, comparable to the 2002 event, especially in size. In this case, there's possibly up to 3,000 deaths, and there was maximum damage to infrastructure. A good portion of San Francisco burned. So in this case, we have two similar hazards as far as size, energy release, magnitude size, and the rupture length here. But the risk from the San Francisco earthquake is much larger, even today, obviously today, as there's more people, than it is for the Denali Fault. So what are some of the potential hazards from Pacific Northwest earthquakes? Well, tsunami are one of the large hazards along the coast, but the shaking from earthquakes can cause landslides, liquefaction, and damage to infrastructure. And this is potentially a much larger risk even than tsunami because of the wider range of people that it can affect. And this is from the Nisqually, 2001 Nisqually earthquake. You can see we've got damage to the road. Here's a water pipe broken. It's actually a water incursion in here from this pond over here. A landslide probably caused by liquefaction. So first of all, tsunami. This is mostly a danger along the coast. This is a result during a megathrust earthquake of a portion of the overriding plate that's offshore, uplifting and causing a wave of water. This is not a cresting wave. It's like a very rapid tidal wave or tide coming in. And I encourage you to look at some of the YouTube videos from the 2011 Tohoku Onu tsunami. It's quite sobering. And so along our coast, here's a tsunami inundation in Willapa Bay. This happens to be my field area. So as you can imagine, when I was out here doing field work, I was very nervous when I was out here. And anytime I camped, I made sure I was in these higher areas because you need to be in an area that's not going to be inundated. And we do have tsunami warning systems out here. You're encouraged to essentially run for the hills. They're also starting to build tsunami structures in areas that are too far away to reach the high ground. However, damage from shaking from megathrust earthquakes, but also from both the deep interplate earthquakes and the upper crustal earthquakes is probably going to cause more damage. So we have slides. These two are from the Nisqually event. This is showing landslides in the Puget Sound area just from the Nisqually event. This is Highway 101 near State Route 8, so right around here. This is right near the Capitol building. This is the trail around the Capitol. And so these landslides occur because of the shaking in wet soils. And this can cause a lot of damage. If you remember, I mentioned in some of the previous work on upper crustal earthquakes, Brian Sherrod actually used trees that were the result of a landslide to get some dates off of this. So they happen a lot. There can also be liquefaction. So liquefaction is when water saturated sediment loses strength as the pore water pressure increases, shaking. So you've probably all experienced this. If you've been out to the coast and you're standing right where the wave wash kind of is, and you're barefooted and you start tapping the sand with your feet, pretty soon you get a little bit of quicksand around your foot. Well, your foot tapping is increasing the pore pressure and causes liquefaction. And so now just think about that on a really large scale. And so this is liquefaction from the Nisqually earthquake. Somewhere below the surface is a sand layer that became liquefied, and it created a sand blow in these cases. It was all around the Seattle area. There's also documentation from people writing about it from the 1872 earthquake in Wenatchee. There were sand blows down closer to the Columbia. So at that time, the river was much lower, right, because we didn't have the dams, and there were sand blows down along the river from this liquefaction. Infrastructure failure is probably one of the scarier aspects of earthquakes. So the Nisqually earthquake caused about $2 million of damage in Seattle alone. Both of these images, this is from this one on the left is from the Loma Prieta, 1989 Loma Prieta earthquake in California, and this is from the 1994 Northridge earthquake in California. I show them because these both stick out, both of these events. I remember them distinctly as a child, and you know, this is showing huge damage to infrastructure. And so earthquakes can damage buildings, they can break sewage and gas and water lines, cause roads and bridges to damage, waterfronts, for example. And these are things that we do know about this. So there's a lot of work going on in Western Washington to try to make sure that we are more prepared so that there's less damage to these things. Some new help to this, I suppose, all along the West Coast is something called Shake Alert. So this is an earthquake early warning system. It's not earthquake prediction, but it's a warning to prepare for shaking. So you have a fault that slips, there's an earthquake. The seismic waves begin radiating away from that epicenter, or the hypocenter rather. And that first wave felt, the P wave, hits a sensor. These are all over the West Coast. The sensor sends a signal to the processing center, Shake Alert, and then a signal goes out to delivery partners and also to phones if you're hooked up to it. So it now just goes out to the normal telephone emergency line if you are set up to receive those. And so what's telling you is that shaking is going to occur momentarily. Depending how far you are from the fault, 10 seconds to maybe a minute at the absolute most. And this is to prepare people so that they can be ready for the shaking. So people driving buses can pull over, surgeons can stop what they're doing, everyone else can move away from brick buildings quickly or get under some kind of cover. Okay, so Shake Alert is pretty cool. You can check it out. And so what do you actually do if there is an earthquake? Well, the first thing to do is when the shaking starts, you drop, you get under cover and you hold on. Okay, so earthquakes cause a lot of things to fall off walls or buildings to start to crumble. You want to get under some kind of cover to keep that from falling on you. So tables, your desk, chairs, whatever. And then you want to hold on so that you and the desk or the table move together as the shaking occurs. You also want to be prepared. This is for all hazards, but have food and clean water for several days, particularly if you're in Western Washington. You may want this to be more like several weeks. Okay, so Western Washington is going to feel the brunt of the mega thrust event. There'll be significantly more shaking in Western Washington than Eastern Washington, Central Washington. Of course, everyone will feel it all across the state, but it will be more severe in Western Washington. And there's also a lot more infrastructure to damage. So having maybe preparation for several weeks. This is, again, not something for Central and Eastern Washington, but knowing how to turn off the natural gas to your house and your neighbor's house is pretty important, because fires due to broken pipes are a major earthquake hazard all around the globe. And having a communication plan with your family and being prepared for several days to weeks of limited cell service is also crucial. And I could tell you this one scares my mom when I have had to say, okay, so in the event of an earthquake, I've let her know I will try to call her right away. And if I can't get through, I'm actually going to turn my phone off, because I don't want it to keep searching for service, lose all of its energy, and then I have no way to charge it back up. And so then I'll try to call in every couple of days. And that, of course, terrifies her. She wants to know instantly if I'll be okay or not. But that's the way it goes. And so with that, perhaps hopefully not dire, hopefully just pragmatic. In this talk, I'm happy to take questions, or if later you think of something, you can email me and talk about any of these things or anything else geologically related you guys are interested in knowing about.
I don't see any questions in the Q&A or the chat, but question I had is, so 421 years, is that where we're at right now?
We're at 321.
Oh, 320.
The last one. Yeah. From 1700 to now.
Okay, 321. All right, so we're not quite there yet, huh? What's the reoccurrence, was it?
Yeah, well, it's 453 years, but it could be 300 to 700. So
okay.
that's why I was in my field area. I'll tell you, I do not sleep out on the beach. I make sure I'm up in the highlands. It may be ridiculous, but what if it happens while I'm out there?
Exactly. All right.
Well, nobody else has any questions here.
Well, I'll just say, what excellent talk, great information. Unfortunately, I wish we would have had more people involved. I'm sure we'd have got a lot more questions. So anyway, thanks.
That's okay. I'm happy talking to a handful or to lots. So
all right.
And maybe at some point when I have more of my research in some coherent form, I'll tell you guys what I've been working on out there. So
okay, great. Thank you.
All right. Yeah, absolutely. I'll see you all later.
Bye-bye.